Okay, here we go. So last time, so real quick announcement. Don't forget about the attendance quiz, attendance code. There it is. You got a little under 2 minutes. Okay, so so back to directional derivatives. Yeah, real quick, I'll remind you of what the point was there. The point was we knew all this stuff about partial derivatives. Partial derivatives only make sense if you're talking about a unit vector. Well, excuse me, got ahead of myself. Partial derivatives only make sense if you're talking about a standard basis vector, but every unit vector is a standard basis vector if you look at it the right way. Right? That's the big observation. That's it. It's ultimately not that deep a point, right? So all of these ideas, all of these things that we can interpret of partial derivatives, it's not that I want you all to think about them as being partial derivatives. It's that I want you to think about all these things equaling to each other. And if this formula representing this computation, representing the answers to these questions, if they all fit together, then might as well capitalize on that. Might as well give them a name. We'll call that a directional derivative, right? And you might say that this is kind of the conceptual interpretation. We're at the point A, moving with velocity v. We want to keep track of how fast the function's changing as we move in that direction. Here's the formula that you're going to compute it with, right? Easy to compute with. For any unit vector, gradients are super easy to compute. Dot products are super easy to compute. And here's the kinds of questions you can answer with it. Excuse me. It'll allow you to compute the slope of the graph. It'll allow you to compute the appropriate multiplicative factor, which, by the way, I think is very naturally understood as df/ds. Okay. All right. Now, I think that's where we ended last time. So let's see some explicit examples. Here's a question you might run across. Perhaps. We've got a function given. Question is, what's the slope of the graph? First cat out of the bag, you're probably thinking partial derivatives. But notice, at the point that we're at, we're not moving in the direction of one of the standard basis vectors, right? We're not going to go in the x direction or in the y direction. We're going to go in a different direction. Kind of a combination direction. In particular, the direction indicated by this vector 3, 4. Now, very important, you do have to recognize, let's go back to here, notice that this does, very importantly, say, unit vector. This idea of directional derivatives, as we've done it, only works for unit vectors, yeah.
Let's just double checking. The exam only have the 2.5, right?
Yeah, talk to me about stuff like that after class. Yeah. But yeah. So only unit vectors, right? I lost my train of thought here. Okay, let's see here. Only unit vectors. So looking at this problem that we have, we cannot use this vector, right? You can't. The rules don't allow it, right? As we've got it set up, you cannot use this vector.
Wait, why can't you use that?
Yeah, okay, because you can only use this construction and with these interpretations as we've defined it when the vector is a unit vector. Yeah. Everybody comfortable with that? Okay. So what are we going to do about that? Well, we're only interested in the direction that this vector points anyway. It's actually really easy to write down the unit vector that points in that same direction. This is now the same direction that we're talking about, and it's a unit vector, so now all of a sudden we're in business and everything is on the table. Is that cool? Is everybody happy with that? Okay, so off we go. We have this idea of a directional derivative. Slope of the graph is something that's computed by the directional derivative, and I'm going to compute the directional derivative by computing with this formula. Right? So again, we just have to say, oh, you want the slope? Fine. Directional derivative does it. And this is how we compute directional derivatives. So note that's what we do here, right? Slope is directional derivative. directional derivatives computed by this formula. Everything else is plug and chug at this point, right? So you do have to compute the gradient, to be fair, right? So the gradient, in particular, the various partials are these. And don't forget to plug in the point in question, right? We're interested in what's happening at that, wrong color. We're interested in what's happening at that point, A. You got to plug in A, and the gradient ends up being just that. You dot it with our unit vector, indicating our direction, and it's over. All right, very good. Okay, let's do one more example. Explicit example. You know what I can do? I can go full screen. That helps. Okay, so we want to compute the temperature. We have the temperature given to us. We want to know how fast does the temperature change as I move in a certain direction. By the way, let's talk about why we would care about such a thing. Why do I care about dTds? Why don't I just talk about where I'm going to, right? And then we'll actually do a linear approximation or something. What's the point of the slope? Of computing this as a derivative. The reason is I might not know yet how far I'm going to go in the direction in question, and I just want to know, look, for every step that I take, how much is the temperature going to increase? All right? So, reasonable thing to want to ask, and again, let's see here. Do it like this. df ds. Compute the directional derivative, which again, we compute with this formula. Right? And everything else is pretty much the same. Yeah, I do have to, got to compute the gradient, take the appropriate partials. Do have to plug in the point. Yeah, a little tedium, right? But then dTds, directional derivative. Directional derivatives are dot product with the gradient. And do the dot product. Don't forget to turn your vector, right? You cannot use a non-unit vector. You have to use that vector divided by its own magnitude to make sure that it's a unit vector. Right? That's the rule, right? That's what we concluded. That's how we constructed this thing. It only makes sense for unit vectors because only unit vectors really are just like standard basis vectors in the way that we chose to look at it. Okay. All right. And then again, arithmetic. Okay, so awkward. This term, directional derivative, this notation, let me do it like this. This term, directional derivative, this notation is sometimes used for a different thing. And I wish it weren't so. I wish there was a consistency of terminology and a consistency of notation. Okay, but sadly there's not. So here's the other take, you might call it, on directional derivatives. The other take is to remove the requirement of it being a unit vector. Now, whoa, hey, slow down, you say. Right? Can you do that? Well, kind of yes and kind of no. Here's the thing. If you go back into here, and if, let's see, I look at here's our definition and interpretations. I want to get the whole thing on the screen here. If you remove the requirement that it be a unit vector, you can no longer interpret your answer as being a slope. You can no longer interpret your answer being a multiplicative factor. You can no longer understand it as being df/ds. All that's gone. Right? But, again, for people who use this phrase and this notation to describe this scenario where we don't require it to be a unit vector, it is still true that it represents what happens when you're at the point A and moving with velocity B and wanting to keep track of how fast the function's changing. That's a very natural thing to want to talk about. even for non-unit vectors. In fact, let's make the observation. If I'm at the point A and moving, what are the odds that my velocity is a unit vector? It is pretty unlikely in practical circumstances, right? So, in fact, there's this, again, very strong case to be made that this is the more natural definition in a way. And it is still true that the answer to that question is still computed by that formula. All right, so this alternative definition of directional derivative is not silly. There are subscribers that prefer this definition, and outside of the context of Math219, I'm one of those people, right? But in Math219, we got to be consistent with the book. The book defines it with unit vectors. By the way, most multivariable calculus textbooks define it unit vectors only because they like these interpretations down here. And by the way, so do we. I mean, yeah, this is really nice. I like it, right? But is it worth having to give up most vectors? And you get a kind of a pro-con thing. And by the way, in more sophisticated mathematical contexts, this is really a small cost, and this is very much the natural choice. Okay, so anyway, I want y'all to be aware of that, right? There is this alternative definition. When you are outside of Math219, you have to be really, really careful about this. You're going to hear somebody you're working with, somebody you're working for, whatever, something you read in a paper. You're going to see the word directional derivative, and who knows, they may or may not mean it in the unit vector sense. That's the world. I didn't do it, right? It's not my fault. But that is the state of affairs. So the unfortunate reality is that you then just have to be on guard, right? You have to look at the context, see, wait a minute, what did they mean here? Look how the calculation proceeds. Are they dividing by a magnitude to ensure it's a unit vector? If they are, okay, then that's a giveaway. Right? If they're not, and if you can see it's not a unit vector, that's another giveaway. Does that make sense? Okay, so again, awkward reality. And by the way, how do you know that this still works? It's actually not hard to show that this still works. It's actually an immediate consequence of the chain rule. It is literally what you get when you apply the matrix form of the chain rule to this little composition of functions. Parametric curve followed by real valued function defined on that space. And you write down the multivariable chain rule, and you get exactly this. Is that cool? All right. Okay, so heads up for that. All right. Some cool things you can do with directional derivatives. Here's a natural question to ask. Let's suppose we're at some point over here, at some point A in the domain. And let's suppose I'm interested in keeping track of how the function changes when I start moving away from that point. The problem is I want to consider all possible directions that I might be moving. Now I emphasize, for the purposes of this question, we're going to consider only unit vectors, and the reason is I only want to entertain directions. Magnitudes, I'm going to say, are not a particularly interesting consideration. And let's just think about why. We kind of know, it's sort of obvious. If you go twice as fast, if I walk twice as fast in the domain, the function's going to change twice as fast in the output. That's obvious and boring, right? So I don't need to consider that part. What's not obvious, what is a complicated, really non-obvious question is, yeah, but whatever speed I plan to walk, which direction should I walk in if I want to make the function increase as fast as possible? Right? So I'm cold, I'm out in the woods, I want to warm up. Which direction do I walk to make the temperature increase as fast as possible? I'm cold, I don't like being cold. Okay. All right, so we are looking for which specifically, which one will give us the maximum possible value, whatever that ends up being, the maximum possible value of the directional derivative. Reasonable question? Yeah? Any clarifications on what the question's asking? Okay, so a little bit of terminology, by the way. So a very common choice of terminology, it goes as follows. We figure if we're maximizing the directional derivative, and if the directional derivative represents slope of a graph, which it does, again, we're looking at unit vectors. All right, you want to maximize the slope. Which direction do I go to maximize the slope? Well, the short version of that is go uphill, right? That's what commonly in hiking circles is called uphill, right? In this circumstance, steepest ascent, same thing, really. It just means uphill. Which direction do I go to gain altitude as fast as possible, right? And so that's what the answer to the question is. This optimal unit vector, that best possible direction, is called the direction of steepest ascent. So that's a reasonable terminology. Here's the problem. That only makes sense if you're looking at a graph of the function, right? And sometimes we are. Sometimes we're looking at a graph of a function of two variables. But the problem, y'all have heard me talk about this at length, very often we're not. Very often I'm not interested in the graph. Or even worse, I can't visualize the graph because it's four-dimensional. Or worse. Right? So that's always been my quibble with this terminology. I feel like it's uncomfortable to call it that. So let's get rid of that interpretation. Forget about slopes now. Let's think about directional derivatives as telling you, look, how fast the function changes per unit distance as you move in whatever direction. If it's telling you how fast the function increases, then the one that makes that as big as possible is the direction in which you're increasing the fastest. So I think the term direction of fastest increase makes loads of sense. In that sort of, take on what we're doing here. Does everybody follow the sort of the formation of these terminologies? All kind of makes sense? Okay. Yeah. So take your pick. Now, cultural note. By far, the more common terminology is this one right here. I'm not super happy about that. It's not my personal preferred terminology. Again, it only makes sense in a narrow context. The nice thing about this terminology here is that it makes sense no matter what the context is. I think it's easier to understand this terminology broadly, right? If you rely on this idea of direction of steepest ascent, you're going to have context problems of, wait a second, I'm not looking at the graph. We're talking about steepest. What is that? Steep? Why is you can see how you get confused. So anyway, heads up, you'll probably hear me say direction of fastest increase in this course most of the time. Outside of this course, you're going to hear the term direction of steepest descent. Okay, all right, now let's solve the problem. It turns out it's actually really easy to solve this problem. This is what I want to maximize. Directional derivative, for which we have a formula, which is a formula with dot products, and this is how you compute dot products. So really, this is what I want to maximize. But wait a second, we're only looking at unit vectors. Unit vectors all have magnitude equal to 1. So this right here is 1. Throw that away. Is that cool? Is everybody with me? So you get right down to it. This is what we want to maximize. Okay, wait a second. It gets even better than that. We have not actually started moving yet. We're at the point A. We are contemplating, maybe I'll go that way, maybe I'll go this way, maybe I don't know which way I'm going to go. But notice I haven't moved yet. I'm still at the point A. For all of the different unit vectors as I contemplate, we're still at the point A. A is not moving. A is constant. Right? And if A is constant, gradient evaluated at A is constant, and therefore the magnitude of the gradient evaluated at A constant. So I don't have to worry about that either. And so here's what it comes down to then all together. Really all I need to maximize, I just need to figure out how to maximize cosine theta, and that's an easy trig problem. Right? Maximized when theta is 0. Yes?
Sorry, could you re-explain why the gradient of f is always constant?
Well, it's constant because it's not literally a constant.
Yeah.
Right? It's formulas, partial derivatives and stuff. But for the purposes of the question we're entertaining, right? So I'm at the point A,
Yeah.
and I'm looking at all these different unit vectors, right? So I'm thinking about, so the vector V is not constant because it could be all these different things, right? But these vectors V, I'm considering all of them from the point A.
Right.
And as I contemplate as the V's are changing, I haven't moved yet. Right? Does that make sense?
Yeah.
Yeah. So A is constant, and therefore the gradient's constant. Yeah. Yes.
So then, let's say it would be constant. Like if A had moved, then there would now be new values.
It would be a dramatically different question. Yeah. And that would completely change how we'd have to approach the question. Yeah. Does that make sense?
Yeah.
Okay. Yeah. Okay. So cosine theta is maximized when theta is 0. Keep in mind, theta is this angle here. It's the angle between these two vectors, the gradient and V. So it's that angle right there, and apparently the answer to the question is just make sure that angle's 0. And I will point out that if this angle is 0, that just means we're looking at the unit vector that points in the same direction that the gradient does. Everybody happy with that? And easy formula there. Then this unit vector, let me do this in the dark green because this is the right answer. This unit vector, this optimal unit vector, is just the unit vector pointing in the direction of the gradient. So, bam. Okay, nice little, I'm going to say 1-2 punch in the sense that we ask a very natural question. Right? Which way makes the function increase the fastest? Sounds pretty broadly applicable. Which way do we go? And the answer is pretty natural. It's a direction that we've already talked about, whichever direction the gradient points. We've been talking about the gradient for a while. Okay, so lovely. By the way, how fast is the function increasing as we go in that direction? Right? Well, again, this is how you compute how fast the function's increasing. Directional derivative, unit vectors only, of course. And let's see, we have the vector, that maximal direction, right? So the direction that we're going to go is that. And then, punch it up. So all you got to do is do the dot product. Wait a minute. A self-dot product is magnitude squared. Oh, wait, one of those cancels with one of those. And the answer, how fast is it? Let me leave that circled. What is this maximal directional derivative? It's the magnitude of the gradient. And so again, a pretty natural question, pretty natural answer. How fast can the function increase? Obviously, something we might naturally want to know. Again, it relates directly back to something we've talked about. So what I really like about this sort of natural pair of questions is that both of the answers, what direction to go and what's the benefit of going in that direction, namely how fast is the function changing per unit distance, they're both just the features of they're the geometric characteristics of the gradient. Direction, magnitude. They are the geometric characteristics that define the gradient as a vector. we can understand the gradient entirely, right? Both in terms of direction and magnitude as answers to these reasonable questions. And so this is a sort of an alternative characterization of the gradient. Makes loads of sense. If you want to have a completely geometric understanding of the gradient, let the record show we have not previously had that. Right? Previously, where did the gradient come from? It was a notational convenience. We were talking about linear approximations, and the notation was clunky. So we've made up a notation to make it easier. Purely algebraic point of view. We now have a purely geometric point of view on the gradient. It's the direction of fastest increase, and the magnitude is the slope. The slope or rate of change with respect to distance, your preference. Okay. All right, so let's do one. These questions do have a little bit of a confusing aspect about them. We're going to talk about that first. So we've got a function here, and we're going to, look at a particular point, and we're going to ask, which way is uphill and how steep is it, right? Now, the short version of the answer to this question, which way is uphill? Oh, well, the direction of the gradient, nothing to it. How steep is it? How steep? Well, that's the directional derivative. That's magnitude of the gradient, right? And you can see that, that's all I did in the answer here is I computed the gradient, and I saw which direction it points. It points that way, and here's the magnitude. So computationally, I'm just literally plugging in for these two things right here. Here's the subtlety. Here's what confuses a lot of students. We have to watch out for the distinction between the point on the hill. I mean, that's where I actually am. Like if I'm out hiking right on the surface of the hill, I hope I didn't fall down into a well and I'm down here in the XY plane, deep underground under the surface of the hill. That would be bad, right? And yet, if you think about it, this down here is the domain. These are the points that we're plugging in to the function. The domain, not this weird Frankenspace made by forming graphs, right? The domain is where the gradient lives. Gradients live in the domain. So we're going to be doing business in the domain. I'm actually up here on the graph. These are not the same points. That's awkward, right? Because I got to tell you where I am, but on the other hand, I got to do business at a point where I'm not. Does that make sense to everybody? In terms of like what the problem is, yes.
Maybe did you just draw like the hill arbitrarily?
Yeah.
Okay.
Oh yeah.
Because I just wouldn't be like.
I'm very open to the possibility that I might have drawn it poorly. I can't quite do the algebra in my head, so yeah, let's not worry about that. But I am highly fallible, and if I'm wrong, thanks for catching. I'll think about it after class. Okay. Right, so here's the thing. Let's again imagine a real world scenario where I'm going to be out hiking around, and I get on my radio and I'm talking to the base camp or whatever. Not that I've ever done any hiking that had a base camp, right? But if I were on the radio talking back to base camp, I would tell them my longitude and latitude, wouldn't I? I'd tell them, my GPS says I'm at, and it would give a longitude and a latitude. I would describe my location way up here on the hill by giving instead the corresponding point in the domain. And I don't think anyone would think that's weird, right? When have you ever heard anyone describe their location by I'm at the following longitude and latitude, I'm at the intersection of this street and that street, and by the way, I am at ground level. right? No one ever says, yeah, I've got, I'm at the intersection of 10th and Main, and I'm 375 feet above sea level. Why would you? Right? This is actually very common. So what I want you all to be aware of, really the only subtle point in this example, is that people will conflate these 2 points. And I think that's perfectly reasonable. And that's how people talk, and the distinction should be clear, right? So it's your job as the person doing the math, right? The sort of the practitioner. When someone tells you the location, they're going to tell you the location here, and you have to understand that that actually means they're on the surface, of course. Does that make sense to everybody? So just you got to think it through. And it can go both ways. Sometimes you'll be given the point on the map, and you need to interpret, okay, that means the point that they're at is actually this point up here. And other times, it might be that what you are given is a point on a graph. And you have to interpret what is the corresponding point in the domain that you will actually do business with. This point down here in the domain is where you evaluate the gradient, for example. Does that make sense? So just for color coding purposes, I'll note, it's this point where you plug in into the gradient. Okay, everybody's happy with that distinction. Okay. All right, here's another nice interpretation, or another nice natural question that we can answer by using the idea of a directional derivative. Less of a question, more of a little exploration that's going to have a nice punchline. But here we go. So suppose we have some level set of a nice function. So we're going to look at this level set where f is a constant value c, some surface. But as I've drawn it, this is a function of 3 variables because the level set is an equation of 3 variables, namely a surface. And let's entertain the question of suppose I'm at this point, and suppose that I am moving in a direction that is tangent to the level set. Right, so this is some little tangent vector. I've drawn the tangent plane just to try to help, conjure the image, to help the picture come to life a little bit. This is a tangent vector to the surface. Okay, well, if I'm at that point and moving in that direction, how fast is the function changing? Another reasonable question, and it turns out it has a really great answer. Here's the thing. If I'm at that point on the surface, if I am moving in a direction tangent to the surface, guess what? I can model that by taking an actual path in the actual surface. Right? So this is what I've drawn in dark green here. This entire curve is completely within this level set. If you think about it, if you're in this level, every point on this dark green curve is on the level set where the function is always c. Everywhere along this curve, the function is constant and therefore not changing. And by the way, check it out. When I get to this point, I am moving in that direction. Right? So I can translate the question of, okay, I'm at the point P and I'm moving in the direction of this tangent vector. I can translate that question to, okay, how fast is the function changing as I move along this dark green curve? And the answer to that question is real easy. How fast is the function changing when the function's constant? Well, when the function's constant, it's not changing. Its rate of change is 0. What do you think? But yeah. Mm-hmm.
But what about any of the other lines? Is it always just...
Oh, well, yeah, if you've been on one of the other tangent vectors? Yeah. So if I picked a different, I'll go ahead and draw that. So if let's talk about this tangent vector. Well, if it's a tangent vector, then I could make some different path. You know, again, starting, remaining, and ending entirely within this curve, or entirely within this surface, for which that now is the tangent vector in the same argument. Yeah. In fact, every tangent vector to the surface is literally a tangent vector to a curve contained in that surface. Okay, so neat fact, these directional derivatives are all zero. Now, who cares? So what? What's the upshot to that? Well, the upshot is actually really nice. If you recall that directional derivatives are computed with that dot product with the gradient, the fact that df ds is zero also means that this dot product is zero. And where have we heard that phrase before? Dot product is equal to zero. What's our knee-jerk reaction? Dot product being zero. Oh, that means those vectors are orthogonal. So we get a really nice conclusion. I mean, this seemingly boring first observation up here immediately tells us gradients are always orthogonal to tangent vectors, to level sets. Very importantly, this was a level set. Right? It's got to be a level set. Okay. All right, and now I just it's all over with the shouting. I mean, the gradient vector. Here's the gradient vector, and it's got to be orthogonal to all of these tangent vectors. It's got to be orthogonal to every tangent vector. What could it possibly be? If it's got to be orthogonal to every tangent vector, I think it would be reasonable to call that orthogonal to the surface. Okay. So that's the nice punchline. And here it is, the little pithy little punchline. Gradients are always orthogonal to level sets. Or in practice, the way we think of this more often, gradients, when they're not zero, which of course would be silly, gradients are perpendicular to level sets. Okay. All right, now there's a quick application of this. It has a lot of details in it. This makes it appropriate for y'all to read through those details. Again, I'm going to hit the highlights. The highlights of this are the question that we're going to answer here is how do we find the tangent plane to the graph? Well, your first thought might be we already know the answer to that question. Tangent planes are the graph, the linear approximation, and we know how to compute linear approximations. That was one of the first things we did. So we already know the answer to this question. What we have here is a different way to approach this question, and I really like how this comes about. The question gets phrased in terms of this surface, let me do it like this, this surface being the graph of some function f. That's how it came to us. It came to us as we're interested in the graph of this function f. And we do this little algebraic fast one. Y'all will recall this from I want to say 2.3. I think it was 2.3. Anyway, whenever you have a graph, you can just kind of subtract and reinterpret as a level set. And now check it out. We have literally a level set of this other new function, z minus f. And as we observed previously, it is a different function. It is not the same function. It doesn't even have the same number of variables. F has two variables, x and y. G has three variables. You can see them right here in the formula, right? X, y, and z. So, importantly, different function. You gotta use the right function if you want to use this argument. And the details for the rest of the argument, I'm mostly going to let y'all read. But the point is, and I made this promise whenever we were talking about the difference between graphs and level sets and interpreting one as different from the other. Sometimes a question will come to you as a question about graphs. but you might find it really convenient to reinterpret it as a question about level sets, and now you can. So we are literally pulling that trick. I'm going to reinterpret this picture up here. Forget about the fact that it came to us as a graph. I'm going to view this as now being a level set of that function, and if I want the equation of the tangent plane, well, I need a normal vector. I need something perpendicular to that tangent plane. Oh, wait a minute, we already have something perpendicular to the tangent plane because we already have something perpendicular to the level set itself. Again, conveniently, it's a level set. Right? So we're just going to take the gradient of g, not f. Very importantly, not f. We're going to take the gradient of g. The gradient of g is literally, I got to shrink this down. Gradient of g is literally the normal vector, and you can just take the appropriate partials, write down that normal vector, plug that into the usual equation of the plane, a couple of details, and out comes the answer that we already knew. So it's a really nice little argument, really cool opportunity to capitalize on the fact that we have a crisp understanding of the difference between graphs and level sets and the relationship, one of the relationships between them, right? And using the calculus of level sets to answer a question that was originally about graphs. Okay, make sure to read the rest of those details. I think it's a healthy exercise. Come to office hours, of course, if you have any questions with that. Likewise, this example, I've entertained removing this example. It's literally exactly what's on the previous page. So I think this is a pretty straight read. Let y'all read that. Okay, we're going to move on now to the implicit function theorem and implicit differentiation. This is a subtle topic. Again, we have to worry about the difference between graphs and level sets. So we've got to be real careful about that distinction. And it's also got this subtlety that we're going to be interested in this idea of a local function. So let's talk about that first. What do I mean? Very importantly, I'm not asking if I can view y as a function of x. By the way, let's just for fun, let's entertain that. Can I view y as a function of x? No, obviously not. Look, I failed the vertical line test. Game over. That question's obvious. That crash and burn. We're asking the more subtle question as follows. When we say a local function, what we mean is whatever point where I'm asking the question, I'm going to look only in a little neighborhood, a little small ball, a little neighborhood of the point in question. So if we want to say, for example, at this point right here, locally, can I view y as being a function of x? Well, locally, the curve that I'm interested in is nothing more than this. Right, now keep in mind, we're local, and because we're local, I am not interested in any of that stuff or any of this stuff. Locally, I'm just looking at that little green piece of curve. Does everybody see what I mean by local? Okay. All right, so for this point, can I view y locally as a function of x? Yeah, sure, no problem. This little green piece of curve right here, all that we're interested in for the local question. Yeah, vertical line test, fine, no problem, all good. So that's nice, and it'd be tempting to say, well, golly, it seems like you could just make that yellow ball, what we call a neighborhood, you could just make that as small as you need it to be. I mean, why can't we just always do this? Doesn't this always work? No. You take a point like this here, right? You look at this neighborhood of this point, and no matter how small you make that yellow ball, the curve that we have to entertain will always fail the vertical line test. Right? Everybody see that? You're losing? Yes.
What if that point was like, I guess, the maximum x value for that curve?
Yep.
So right at the point where it
Yeah,
comes,
that's-
wouldn't it pass the vertical line?
No, it fails. That is exactly what I was intending to draw. Is exactly the point that's, you know, in around here anyway, as far as you can go to the right. And the point is, it's perfectly vertical there, right? And if you therefore look at the neighborhood, you're going to have this part here kind of wraps over to the left, but this part down here kind of wraps over to the left also, and so the vertical line is going to be able to hit two different points. Yeah, so that's the problem.
I guess because you were saying it doesn't matter how small we make it.
Yeah.
If we do make it as small as possible, it would only go through that point and it would pass the test.
So it
What's
has
the
to.
definition of as
Yeah, no, that's a great question. So it is required that this be an open ball, and an open ball cannot have a radius of 0. If it has a radius of 0, it'd be just a point, and it's not open. Does that make sense?
Yeah.
Yeah, it's a great question. So yeah, non-zero radius, but as small, as long as it's not 0, as small as you want. Yeah. Okay. All right. So that's the problem. So can we view y locally as a function? And the answer is usually yes. Most points, yes. But at some points, no. And by the way, this point over here, also, no. Is everybody happy? Now, again, the looming question, who cares? Why are we interested in this? What's the point, right? Is this just silly math games? No, it's really not silly math games, because this question answers another question that I think y'all will all immediately care about, and that is, wouldn't you like to be able to talk about dy dx? Right, dy dx is cool, right? It's valuable. You can do a lot of neat stuff with dy dx. We need to be able to compute dy dx. And here's the problem. I don't want to go around writing down dy dx as if that's a thing. If it turns out that I'm interested in a point where it's not defined at all, right? So don't make the mistake of thinking that, oh yeah, at a point like that, like dy dx is infinity or something. No, that's not a real number. Infinity is not a real number. Right? Is everybody comfortable with that? I hope everybody knows infinity is not a real number, right? So at a point like this, dy dx is undefined. If you are at a point like this, let me rephrase that. If you have not yet established that you are not at a point like this, in other words, if you may be at a point like this and you're writing down dy dx willy-nilly, you're writing down a bunch of garbage. I'm just saying, right? Everybody see the problem? Mathematicians are real uptight about stuff like this, and I think this is rightly so. Right? We like to be able to say that when we write down math that we're quite sure it's not garbage. Right? It's a good thing. So that's the thing. You've got to be able to establish that we're looking at points like these, that we are not looking at points like these before we can even talk about dy dx. Okay. All right. So how do you do it? Really nice little argument here. I mean, we already sort of talked about the problem is when the curve wraps under itself. I mean, the whole reason that this point's a problem is because when I try to do the vertical line test thing, I'm going to have a self-intersection, and you have that self-intersection because the curve, again, it kind of wrapped under itself, I think is a good way to think about it. Further geometric claim, that happens, that is possible only if you have a vertical tangent line. And by the way, don't forget that gradients are always perpendicular to level sets. Now, quick reminder, we are talking about a level set here, right? We were initially talking about a level set. And gradients are always perpendicular to level sets. And if we have a vertical tangent line, then we have a horizontal gradient, and that means the y partial would be 0. So what we have is the makings of a good test here And let me do it like this. If we have a problem, that partial will be 0. And so now let me rephrase that. And again, I'm going to use the contrapositive. I've talked about the contrapositive before, right? It's a really useful construction. If P implies Q, then not Q implies not P. In this case, if that partial's not 0, no problem. So that's this is our first example of the implicit function theorem. By the way, single variable calculus classes, and especially high school single variable calculus classes, will take situations like this where you're looking at a level set, and they'll just go right on into talking about dy, dx, this and that, as if that's cool, right? And awkward. I mean, that's not good, right? They were playing with fire. They didn't take appropriate precautions. Right? So we now have the appropriate precautions. Just compute the y partial, confirm it's not 0, and then go about your business. Okay, well, we'll pick up here next time. I think we're out of time now. Y'all have a good one. See you later. See you on Friday. Don't forget, test on Friday. Same location, same time. Yep, I got it. Yep. All right, see y'all later.
What?